Okay, cool. We're back. And goal for today is kind of work on getting any kind of questions and troubleshooting that we have for project 3. So hopefully we can like wrap up module 3, move on. Yeah.
We got a question on the third problem of project 3.
Okay. So in the third problem, I'm jumping down here. Yeah, where we're trying to.
So the problem I'm having, I get the concept where you're creating a function f of dm.
Okay.
Because you're going to solve for the mass change rate. You're essentially leaving that as the variable to solve for. You set the function equal to 0 when it's the height of 300 minus whatever that function is.
Okay.
The problem I'm having when I try and run the code is in the time space variable, so nv.len space, you have to use that mass change rate as part of that. Because you use your endpoint.
Yeah.
Start minus, or ending minus starting.
Okay. Yep.
And it's giving me errors every time I run this thing.
All right. So let's try to build. I have like, do I have Simple Rocket built out? No, I don't. But we can build that pretty quick.
I think this one uses the rocket function though.
Yeah, I was just gonna shoot. Yeah. As long as we have like something. Over m. Oh. State bracket 2 times dt. Oh, Simple Rocket, missing state. Oh, yeah. There. All right, so first I just want to make sure that my answers are kind of doing what I wanted. And like if you're working on problem 3, you've already gone through those first couple of steps, but if I'm plotting like mass versus speed, I should be seeing like some kind of log plot. So if I just look at like the solutions that I have so far, and then I could look at y bracket 2 and then negative u times the log too many parentheses. U is 250. Make sure I have everything defined. So even if I'm not showing like a smooth curve with like that solve IVP, I can show that that log function is what I'm getting. And once I have like a method that I know that I can integrate with, then I can start changing it and figure it. And now I could like optimize for, can I reach 300 meters with Simple Rocket, add gravity, still reach that. So if I'm looking at like what did I need to get the state at that last point in time? So like when the rocket will explode, the things that I really needed were like this DMDT is going to be my function input. It gets used in defining time. Like if I want to know how long I need to burn, then I need to know what that final mass is at a given burn rate. And that gets plugged in here into my simple rocket equation or my rocket equation. And then I can get like that state that way. So I'm going to take this whole thing. Oh, let's just copy all this. I'll bring it down into my like FDM kind of work. Bless you. Thank you. So M0 is one of my inputs. So I don't want to, I mean, if I want, I could, yeah, so right now it's a default value. So I don't want to set it inside the function. Like, and I've seen this before, like people are trying to like get their function to work right, and you can hack your way through it and like set variables inside the function to be certain values, but then whenever you change them as an input, they get overwritten. So I don't want to overwrite the thing that I'm already writing there. So I'm commenting that one. Mass final is gonna be that 0.05. I don't want to overwrite that DMDT because that is that's what I'm trying to like find the value for. So I want that to be an input. I don't want to overwrite that one, right? Because that's one of my inputs as well. I'm just zooming out so we can see the whole function. And really, I don't need this whole time. All I really need is like time final. And I could just calculate it like this, where DMDT is that value that I'm trying to calculate at, like the height at TF. And then instead of going 0 to T negative 1, I'll just go 0 to TF, make some final time. So now I can say error is sol dot y bracket 0, comma negative 1, and minus 300. And I get 297 meters. So that means that the height that I calculated at that time was 297 meters above 300. That's what I have so far. And if I go back up to this first solution that I was working on, I can double check that and say plt.plot sol.t and sol.y 0. And now I can see that I'm hitting about 600 meters at that final 4 seconds, because we're gonna, at 0.05, we're burning for 4 seconds to get through a fifth of a kilogram, 200 grams. So 297, pretty close to 300, 600 minus 300. Seems like I'm on the right track. Then the real way to test it is like, if I change it, is it, so 0.1, I get a different value. So it's not, I am changing the DMDT there. I'm pretty, at least it seems like I am. Yeah.
Can you explain the syntax of the sol IDB? Because also you're setting your parameter in simple rocket to DMDT equals DM, but there's no longer a DM variable.
Oh, you're right. Yeah, there should be a
should just DMDT equals
DMDT. Yeah. 0.1. Yeah, so that was probably using the old value of dm. So let's go back up here, see if we can change like that. dm to 0.1. See what we get. Yeah, so it's about 300 at 0.1. So it seemed, if we change that dm dt to 0.1, at least for the simple rocket, it seems to be about 300 meters high. If you ignore
the syntax or just the solve IVP input.
Oh, yeah. Yeah, like how do I use solve IVP? And so you don't have to. You can use any of the integration methods that we've used so far. It's just that this one, most people don't rewrite integration methods because they've been around for 80 years now, and there's lots of built-in methods for them. So let's walk through kind of the step-by-steps of solve IVP. In this first line, I'm just trying to define a function that's a function of time and state. The state could be as big or as small as I need it to be. Right now it has 3 values in it: height, velocity, mass. It could have height, velocity, mass, x position, x velocity, pressure. Like, you could have as many things in there as you want, as long as you have differential equations to describe this is how they're changing. So y is as big of a vector as you need it to be to describe like all the things that are connected to your differential equations. So that's that first line, that first input. This next input is define, can't spell, define time span, start to stop, and you're just giving it the upper and lower, the lower and upper bounds in that one. Solve IVP is going to step through and figure out, like, can I take a large time step or can I do a small one based on what the derivatives are? And it's got an algorithm in the background to figure that out. And then the last thing, well, it's not the last because you can add as much as you want. The last part is define initial state. And your initial state has to be the right dimensions. So if I have 3 values in my state, then I need an initial state that has all 3 values defined for that. Because this is an initial value problem, we need initial, in this case, position, velocity, and mass. And then we can integrate all 3 of those from there. And then the other thing that I like to do sometimes is like this t eval equals t, where this is define points in time you want solution. This one's not as important for that like FDM function because we're only looking at the final time. But here, if you want a smooth function, like if I want to actually see what's happening between 400 and 100 meters per second, then I can say t eval has 50 steps, and then I see I have a uniform spacing for that. Yeah.
When you're calling that function sol.t,
yeah,
sol.y, that means it's finding the time values and then the
OEM.
The y outputs basically.
Yeah, so let's take a look at the actual output. So and then solve IVP, like when you get a solution, it'll tell you information about what happened during that integration process. Success, usually it says true unless something weird happened and like it couldn't get to the final time step that you asked for, which might happen in this case. Like if you ask for time when mass becomes negative, you might say it might give you as much as it can, but just kind of fail out. Then number of function evaluations, like a bunch of stuff that normally we don't have to look at, but the t, that value of t, in this case I was giving it like specific t eval points, like these are the points that I want time evaluated at. Sometimes it's different time steps in there, and then y are all the states for, and this one it's a little different than the way, because normally what we do is say every row is a point in time. This one says every column is a point in time. So if you look at sol dot y, let's dot shape, instead of having 50 rows and 3 columns, we have 3 rows and 50 columns, but it's the same output that we had been creating, like create a state, initialize the first one, then step through all the other points in time.
When you call it, you just split the indices basically.
Yeah.
So instead of doing, the first one being your,
yeah, instead of saying that this is my first point in time, this is saying this is my first state. So y0.
The last value of that state, 0, -1.
Yeah. So that is my final height, at least in this simple rocket, for 0.1 kilogram per second.
So then there'd be no difference calling the rocket function, basically, in that we made
No.
it at the end.
Yeah.
You just change the function name.
Yep.
And it should spit out the same thing.
Yeah, that's the beauty of like doing all that initial work of like making sure you can converge to something, and you've done all the hard work of getting things to work, and then the next part is just kind of changing variable names.
Can you explain the lambda t comma y?
Like why?
Yeah, why that's used.
Why here? In general, you always need time and state for a differential equation. In this class, we've only dealt with differential equations that are a function of the state. So everything is either position or velocity functions. But you could have a forcing function that's a function of time. You can have all sorts of things that are functions of time. Even the mass that we have programmed in here, we could turn that into more of like mass as a function of time, and get rid of it out of our state values if we wanted. Or we could say that it's a dm dt over time, like have that be a function of time. Or mass, I guess then it's a function of the... So anyway, because you always need t and y in your differential equations, I have to tell solve IVP what to do with time.
Does it matter the order?
It does, yeah, because if I try to say y comma t, it's going to tell me that it doesn't know how to take a subscript of time of t, because it's yeah, it shows me where it's happening, and it's kind of hard to decipher, but the background, the reason that it's giving me this error and pointing here is that it's trying to plug in a value of time like 0 and take the first index of the number 0, but numbers don't have indices. Yeah, so the order, it's got to be t then y. Yeah. In this first one, Yeah, this one we said like 0.05. Yeah. Um, yeah, I think that's what we said for, at least for this like first. For this first thing, that DMDT is 0.05. Nice. Yep. Yeah.
Why I would like this state, I mean this state to be negative DMDT, where the function above state is positive.
Yeah. Yeah, because the acceleration that you get is so the thrust is a positive thrust, like it's pushing you upwards with the more mass you push out, but the amount of mass that you lost for that amount of thrust is a negative DMDT. So your mass, the change in your mass is DMDT times dt, like negative DMDT. Yeah. Otherwise, things start to look a little weird. Yeah, this is my like positive DMDT function. And whenever I look at like how high it got, it looks like it's still going up. But yeah, it looks like it's slowing down somehow. Yeah. Because this is almost like imagining you have like a vacuum cleaner that is creating thrust somehow. Because the more thrust you generate, the more mass you gather. So it gets harder and harder to push your spacecraft. Yeah.
I got a question on the last part of number 2 for this problem, where it's talking about now you're factoring in gravity and drag in the rocket function.
Yeah.
So I can calculate the implicit and explicit numerical solutions.
Okay.
How do we plot the analytical solution? Because we're only given the simplified equation.
Yeah, and it's
because my numerical solutions don't converge to the simplified equation because that one doesn't include drag and
yeah, and
gravity.
And it should not converge to the same thing. All right, so I'm gonna say I'm doing everything right. So I'm gonna come down to problem 2 and just start changing the things that I want to update. And then I'm gonna grab my rocket equation. Oh yeah. And I'm doing everything right. Sorry. So default for solve IVP, default is that it's a explicit method. So it integrates. I'm not matching this analytical function anymore because I'm including drag and gravity. And that makes sense. Like it shouldn't match unless the force of thrust is much bigger than gravity and drag. So the way that we can test that out, at least if you want it to converge, it doesn't matter to me, as long as the two methods converge with each other, like explicit, implicit, then it's fine. But if you're like, well, how do I know that that this thing is working? Let's turn this thing, instead of just like slowly burning it, like full thrust, and start decreasing the value, like the relative weight of gravity drag. So turn this into 1 kilogram, basically a bomb exploding at this point. If you're burning 1 kilogram per second, and now when we plot it, it's pretty close to that ideal solution that thrust is the biggest force. So it does make sense, like we can get back to that convergence criteria. And again, like if you always do this kind of process, like think about, all right, how do I get it to match a known solution, even if I didn't make the solution, like some other, I can look it up, find some function for it, see if I can match it. And you'll save yourself a lot of headache, because these kind of problems are easier to troubleshoot in small pieces. And if you want really, like, yeah, by the time we're burning 10 kilograms per second, and that's a lot of thrust for this tiny little rocket. It's also time, the whole explosion, the whole thing happens in about half a second, I think. No, I think even less than that. Let's see, how high do we get? It lasts 20 milliseconds and it reaches 3 meters high. So this thing, if you're burning at 10 kilograms per second, you basically lit off like a, what am I thinking of? Like a bottle rocket? Yeah, just like a bottle rocket that just shot up and it's blowing up at your ear, like a little above your head. Definitely not our 300 meters that we were aiming for, but it does match. If thrust is big enough, gravity don't matter. Which does bring up, so here, this one, so the last thing that we didn't really talk about was we can define what integration method we want with solve IVP. So if I want an imp method, like implicit, or like mixel-click imp, I don't know, then I can look up what methods are available in the solve IVP methods. And if I don't like any of them, it's open source, I can always write my own. So again, default is this Runge-Kutta 4-5 method. As we come down to functions, we can see that this is in fact an explicit method. So there's no check. It's not going to stop and check before it moves on to the next time step. And a lot of these are explicit. Like here's another Runge-Kutta explicit method, another explicit Runge-Kutta, versus like Redau is an implicit Runge-Kutta. So it'll do something to check before it moves on to the next time step. And then BDF, same thing, implicit multi-step. And then LSODA, that one I would have to look up, the Atoms BDF. I don't remember if Atoms, and I don't remember if that one's implicit or explicit. So let's try Redao. I put these RKs in the wrong spot. Oh. And there, I can't tell the difference between all three solutions, so something's right. I can always subtract, right? Now I can see a little bit more of like what the difference is. Circles are the implicit, squares are the explicit. Initially, there's no, again, we're kind of reading this backwards, right? We start at 0.25, we move to the left until we hit 0.05. So initially, there's no difference in the integration methods, but explicit methods, that they tend to have a little bit more error. Meanwhile, implicit usually has less error. They're better at things like trying for conservation of energy. Implicit methods would be better at making sure you actually conserve energy. Bless you. Yeah.
When I'm doing the last problem, putting in the solve IDP function, I'm getting an error that says only size 1 arrays can be converted to Python scalars, as I'm trying to call the ink search method, basically with the new bounds.
Oh, with ink search. Okay, yeah. All right, so we've got mod ccan in here, but we want to run over and grab ink search, right? All right, I can reproduce that. Is this ink search? No. And then we just need like some values, like 0.05, 0. I'll go up to 1 and maybe 10 iterations. So if I'm looking at like trying to trace out where does this error pop up, again, I like to start at the bottom, and in here it's telling me this, which is not super helpful, and then showing me in here like somehow it's trying to plug it into this value and it's not doing the right thing. So when I'm running that function, that solve IVP is not working correctly. And then as I come back up here, it's telling me at this line, when I'm trying to take X and plug in a lot of different DMDT values, it's not working. So let's try just that. We'll say DM vals is we'll just give it two values. And it recreates that same type error that something's wrong when we try to give this thing an array of values. So instead of trying to do it all in one line, really what I want to say is like create the thing I want to create like a list of values by just running one thing at a time. So I can do it with like list comprehension or a for loop of like just evaluating one DMDT at a time, which means up in here, I want to change this function of X to like some function of Xi for Xi in X. I'm gonna make an array so I can actually do like NumPy stuff on it. Now when I try it, it should work. And give it an initial value, maybe 10 steps. So now I get one bracket. I don't like that it's so close to my boundary. There we go. That's a little better. I don't like when it tells me something, it's like the solution is at the boundary of where I told it to look. It just feels like something's wrong.
Can you explain what you just did back in the ink search function? You changed the line where it was f equals, yeah, it used to be function of x.
Yeah. So that works great if you have a function that you can plug in as many values as you want, like sine of, if your function is sine, then yeah, go for it, go nuts. But when we're starting to define these like numerical functions where we can only give it one DMDT at a time, otherwise it gets kind of complicated on how we're going to deal with multiple DMDTs, like, because really if we wanted to do that, we'd have to like create our own for like if else statement, like if DMDT is length of 1, do this, else take one value at a time, plug it in, rather than just saying like, okay, just evaluate the function one at a time and then stick them all into one array anyway at the end of the day.
So is that why I'm getting a different error when I do the modified secant function? Because it's no longer the same error as the ink search one.
That
I
one,
think it's still running into the same issue where it's not, you're trying to iterate over a time step that isn't defined quite yet.
I think mod secant should work. And then limits are. So we need a dx and then an x0. That one works out of the box for me.
Okay, the x0 set incorrectly. The x0 set way too high.
Oh, this, yeah, I guess if you...
I copied it over from a different example and it should be 7. Just work.
7, yeah, because... Yeah, and there we ran into the same kind of problem in the homework with Newton-Raphson. Like, there's only, whenever you have like these are called open methods, modified secant, Newton-Raphson. Open methods have no check to make sure that they stay in the bounds of what's physical. So it has no problem plugging in like a negative dm/dt, but now it's gonna have like a weird value of time, like time is going backwards, and then we'll start getting infinite numbers and nada numbers and things like that. So whenever, like real root finders, they use a mix of bracketing and modified secant or Newton-Raphson. But we're just kind of doing one at a time to see what the limits of root finding are. Yeah, if it's too big. And even, yeah, if you do something like 0, it's not going to work either. Or if it's really small. Oh, really small seems to work. We'll get there. And again, I'm still using like simple rocket in my root finding method.
If you want to use Euler's step instead of the solve IDP, how would you modify that inside the actual function of the end? Because you have to use a for loop.
Yep.
But again, the for loop is evaluated over time steps that are yet to be defined because we don't know dm/dt.
But dm/dt is
what we're solving for.
It's what you're solving for, but if you know that it is a value, you can figure out what the time step is, what the last time is. So here, I can still use the exact same kind of setup.
Okay.
And then say t is linspace 0 to
because that's what I've done.
tf.
Yeah.
And however many time steps I find converges correctly. I guess really we should use something like a range, start, stop, step size, where dt is like some known value that we know it's going to work, and add like dt over 2 to that final step so that tf is included in that last value. I always hesitate to use, I guess, yeah, I always hesitate to use a range because there's like weird cases. np.a range 0 to 0.2. There's some weird cases where sometimes the stopping value is included, other times it's not included. It's not supposed to be included, but sometimes 0.2, does that work? I can't remember. Anyway, but a range would be a good function for this, because we know there's probably like some delta t that works where it's converged, and we want to get to that final value, so that would work. and then we would want to say,
Because Andrews did the simple version of, previous solution plus state times the. Did we define DT?
DT, I haven't defined it.
Because I pull it from previously.
Yeah. Do I want to put it? Maybe I want to put it as a 0.1 second. 0.01 seconds. And here, like if you want, we could say state is like we can just update the state and not actually keep track of it in the function. Like if we're doing everything kind of our own way, we can just overwrite the state with the new state.
But if you wanted to plot it, you would then have to plug it into that for loop then, correct?
Yeah, well, inside this function, this whole state array is going to get thrown out anyway, unless you return it with error.
Yeah.
So that's why when I'm looking at it, like, well,
mostly just because one of the questions asking to plot.
Yeah.
So you would need to somehow spit out those intermediate steps.
Yeah, but those would be like other things that you're doing. But as far as like defining this FDM function, I don't need all the values of state. All I need is the last one.
Mm-hmm.
Oh. Yeah, and I still get the same values that I was getting before. Yeah, 297, as long as my DT is small enough. Cool. That was fun. Oh, and we're out of time. That's why. It was too much fun. All right. Thanks. I'll see you again on Wednesday.